Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Okay, so today we proceed with another techniques in digital modulation, that is frequency shift keying (FSK). Okay, as introduction, frequency shift keying is a digital modulation technique in which the frequency of the carrier signal varies according to the digital signal's changes, and the output of SXK modulated wave is high frequency for 1 bit. So if the digital bit is 101010, so for the 1 bit it in the FSK modulation is the high frequency, and for the 0 is low frequency, like this. For example, here the 1 you will have high frequency here, and 0 low frequency, 1 is high frequency, and so on. So there are two frequencies that use, the F1 and F2. Okay, the generation of FSK waveform at the transmitter can be achieved by generating two ASK waveform. Okay, previously you have learned about the ASK, how the amplitude shift keying generate. That's the FM multiply with the local oscillator. So this one have the same technique, but it use two ASK waveform. So the ASK waveform with low frequency and high frequency. Okay, for the low frequency, it's represent, okay, for example, you have the signal of, okay, for example, here is 0 1 0. Okay, actually this one for the, okay, the information signal is 0 1 0, the VMT 0 1 0, and then this frequency will have the 101 multiplied with the low frequency to generate the low frequency here. For example, actually this is the actual is 0 1 0, but to generate the low frequency, this low frequency from the local oscillator multiply with 101 to generate this one, and then it's multiply with the original 0 1 0 with the high frequency to generate the high frequency, and then it's sum together for the ASK1 and ASK2. So it's the output is FSK of 0 1 0, where the low frequency represent the 0 bit and high frequency represent the higher bit. Okay, this is in the time domain. For the frequency domain, so we have two frequency for the omega 1 and omega 2, because for the FSK there are two frequency. This is F1 and F2, and then it's can combine in the omega 1 and omega 2. And after okay, for the frequency spectrum of the frequency shift keying FSK, Okay, as I explained before, that the FSK waveform is generated by two um, two ASK waveform because we have two frequency, F1 and F2. Okay, this is the time domain frequency, and this is frequency domain spectrum. Okay, we have for the FSK, we have two signal with the same amplitude, same phase but different frequency, with the low frequency and high frequency. For the low frequency is for the bit 0 and high frequency for bit 1. Okay, for this example, this one you have okay, we have the information signal of 0 0 1 0, and then um, at the low frequency it will invert the coding, so we have 101 to result in the frequency like this, that we have low frequency, no frequency, and then another low frequency, and then this is the bit from the original signal. We have 0 1 0, and the 1 will result in the high frequency spectrum. Okay, and then these two signal with different frequency with combined by multiplier will result in the FSK. That is, we have two kind of frequency, the low frequency for the 0 and high frequency for 1. Okay, this is the frequency domain of this spectrum. Okay, because we have two different frequency, so we have omega C1 and omega C2, and this one is the frequency spectrum of the carrier, because carrier we have two frequency of two frequency of carrier signal. We have omega C1 and omega C2, and then this is the frequency of information signal. Okay, because this is digital signal, we have three bits here, and we have three spectrum here, and combine both we have this spectrum frequency of the FSK. Okay, this one is how we reproduced it. Okay, this is one of the example of how to generate the frequency shift keying signal. So we have the digital input of 101, and then it's go through as V1, and then V1 will multiply with F1, the frequency 1, then this is the high frequency, and then from the information digital input of 101, it's invert to get the second signal with low frequency. So invert this, and we have 0 1 0 multiplied by the signal from oscillator F2. So we have the uh, low frequency, this is the high frequency, and then summation of these two, we will have the FSK here. Okay, for the V1, V1 is actually the VM from the input. And for after inverter, it will go through minus Vm1t. So after that, okay, for the for the digital signal, the equation is 1 over 2 plus 2 pi multiplied by cos omega mt minus 1 over 3 cos 3 omega mt plus 1 over 5 cos 5 omega mt. So this is the equation for the digital signal. And then, okay, this is after inverted. Okay, we multiply both we see the carrier frequency with f1 and f2. So we have vfsk is the long equation like this. Okay, for the bandwidth of the fsk, for example, we have the okay, for the bandwidth of frequency shift keying, if uh, the signal have third harmonic, so that's mean for the bandwidth for FSK signal, if up to third harmonic, if we have like previously we have 0 1 0 1 0 1, so for after the third harmonic, the formula for FSK is 3 Fm plus 2 delta F plus 3 Fm, or 6 Fm, because the FB, okay, 6 Fm plus 2 theta F, or 3 times FB plus 2 delta F, because the FB is 2 Fm. So this is the simplification. And for the basic requirement, the bandwidth is from here to here. This is the FB plus 2 delta F. Okay, FB is 2 FM. This is FM and another FM. So we have FB there, and then delta F is FC2 minus FC1 over 2. This is the formula for delta F. And to generate the frequency shift keying, there are three methods that can generate the shift keying. The first method is using a multiplier, where okay, this one we have modulator 1 and modulator 2. So from the, okay, this is the carrier input F2 and carrier input F1. This is the inverted data stream, and this is data stream. Okay, this one is same like I explained before. This actually same with this. Same with this. Okay, this is in the block diagram like this, and then this is the multiplier, summing the amplifier both of this, and we get, okay, this one is we get for the high frequency, and then low frequency, and the output we have the combination of high and low frequency. Okay, another one. Okay, the second is use the switch, the on off switch. Okay, for this for this technique, if the switch is off, the carrier frequency FC2 will operate. Okay, this means is the switch is closed or off. The FC2 will operate, and then when the switch is open, the frequency signal FC1 will function. Open, the FC1 will function. So this open and close switch will result in two different frequency signal. So the output we have frequency with FC1 and FC2. So the switching action will produce two different frequency accordingly. Okay, another way is the third method to generate the FSK is by using voltage control oscillator VCO. Okay, this device is suitable because it can change the frequency when the amplitude of the voltage is applied to it. So we have the information signal pass through the low pass filter, and if the voltage is maximum, then a different frequency will be generated. So for example, if voltage is zero, okay, voltage if voltage is zero, it produces frequency. If voltage is maximum, is 1, then different frequency will be generated. So by using FSK, we also can generate the frequency shifting signal. Okay, so there are three methods that you can use to generate the FSK. Okay, for the receiver of the FSK, okay, so previously generate is how to generate from the digital to analog, but for the receiver is demodulate. This receiver is same as demodulation, that is from the analog to digital again. So there are two methods that you can use in for the receive the FSK signal. That is asynchronous method and synchronous method. For the asynchronous method, it will use two filter and logic comparator. So this type of receiver use two filter tuned to two different frequencies. So the first one is omega C plus delta omega, and the second one is omega C minus delta omega. So after go through this filter, okay, the filter with high output indicate either the logic is 1 or 0. So this logic comparator, for the high frequency, it will create uh, the logic 1, and then for the low frequency, it will generate 0. So we will get back the VM, that is the digital signal. Okay. The second method is the synchronous receiver. So for the synchronous receiver, the FSK signal will multiply with the signal of cos omega C plus delta omega T and cos omega C minus delta omega T, and after that both of these output will be go through the different. Okay, this is the differential amplifier, and after go through the differential amplifier, it will go through the low pass filter. That this low pass filter will allow the signal EC over 2 or EC negative EC over 2 digit, representing the signal to pass through. So and then the output is digital signal. Okay, this is the two method of FSK receiver. And for each receiver, asynchronous and synchronous, the noise different. We apply different formula for the two types of receiver. For the asynchronous receiver, the possibility of error equal to 1 over 2 e power of negative EB over 2NO. Okay, and the EB equal to EC squared T over 2. Okay, this is the equation for the noise of a synchronous receiver. And for the synchronous receiver, okay, before that, the synchronous, also known as coherent, and asynchronous known as non-coherent. Okay, and for the synchronous noise, the noise is 1 over 2 ERFC. The X is 0.5 EB over NO. So this one from the table of error function lie in the amplitude shift keying. Okay, for the first example, an asynchronous FSK system is modulated by a digital signal and operate at 10 MHz. The frequency, okay, this is the signal of the modulated digital. Okay, this is FSK. The frequency deviation delta D is 850 Hz, and the bit range is 110 bit per second. So the peak to peak carrier signal is 2 volt, and the noise power spectrum density for 2 band is 1 multiplied by 10 power of negative 4 watt square over hertz. Calculate the BER. Okay, BER also same as PE. So this is the asynchronous system. So the PE or BER equal 1 over 2 e power of negative EB to NO. Okay, so the EB equal to EC squared T over 2 and EC equal to EPP over 2. So given, okay, let's see what is given here. EB, okay, EB from EC, EC from EPP, and this peak to peak signal is 2 volt. So EPP equal to 2. So the EC equal to 1 volt. Okay, so this of this, and then T here. Okay, T, okay, T is period for the, okay, this one is receiver, so we will receive back the digital signal. So for digital signal, we use the unit of bit per second. Okay, because there is two things. There are 1, 2, 3. There are 2 frequency and 1 bits per second. But bear in mind, this is digital signal. This is modulated by digital signal. And the T is 1 over FB, whereas the FB is 110. So you will get the T is 9.09 times 10 power of negative 3 second. Okay, we already have EC T. Okay, you can get the EB. EP equal 1 squared minus 9 power 09 negative 3 over 2 over 2. So you will get the EB is 455 times 10 power of negative 3. Okay, the unit of EB is joule. Okay, this one 2 N naught. So N naught is the noise power spectrum for one band. So the given here, this one is given for 2 band. That is 1 times 10 power of negative 4. So the okay, N naught over 2 equal 1 times 10 power of negative 4. So you will get the N naught is 2 times 10 power of negative 4. Okay, the PE is 1 over 2 E power of all this. So EP, you get this one is EP 455 times 10 power of negative 3, and then 2 times N naught. N naught is, okay, this is N, okay, this one is N naught. Okay, negative 4. Okay, this one is power exponential negative. So you will get the answer if 5.7 times 10 power of negative 4. Okay, so this is the BER of the system. Okay, this is the BER of the system. Okay, this is